Good morning. Thank you for joining us for the third and final day of the 22nd Annual New Jersey Department of Transportation Virtual Research Showcase. Our agenda today features transportation-related research projects sponsored by organizations such as the NJDOT and others. We will have 3 presentations, then a short break. When we reconvene, we will have 3 more presentations and part 3 of our virtual poster session. Please use the chat pod for questions. At the conclusion of each presentation, the speaker will have an opportunity to address your questions. If we run out of time, your question may be answered at a later time. Our first presentation is exploring the impacts of VMT-induced PM 2.5 on the rate of COVID-19 infections, presented by Dr. Igana Harry and Hojat Baruz of Stevens Institute of Technology.
Thank you so much. Good morning, everyone. My name is Igana Harry. I'm a faculty at Stevens School of Systems and Enterprises. We are presenting this work with one of my master's students, Mr. Hojat Behruz, and we are going to share with you what we have found out on the potential impacts of VMT-induced PM 2.5 on the rate of coronavirus or COVID-19 infection. Next slide, please. Thank you. So a little bit about the motivation behind this study. We all know that the combustion of fossil fuel results in many different types of emissions. Annually, there are 4.2 million deaths around the globe due to air pollution emissions. Within the transportation community, we have been concerned about these pollution emissions over the last couple decades. However, we all know that most of this focus has been on greenhouse gas emissions and climate change in general. For this particular study, we are focusing only on PM 2.5 and the health impacts, not so much of climate change, but the health impacts of PM 2.5 resulting from vehicle miles traveled. Next slide, please. Okay, so let me tell you a little bit about PM 2.5 before we go into this. First of all, I would like to point out that not all pollutants are equally harmful. Emissions of fine particulate matter, ammonia, VOC, sulfur dioxide, they make up only half of all emissions by weight, but cause almost 80% of total damages. Focusing only on PM 2.5, it accounts for only 6% of total emissions by weight, but causes 23% of total damage. If you look at the figure on this slide, you see that towards the left, if you can find in one of the big oval particulate matter, you see that it is associated with a large area going to or directing to respiratory illnesses. And all of us know that today when we talk about respiratory illnesses, the first thing coming to mind is coronavirus and everything else that we have been experiencing due to this pandemic. Would you please click? Okay, so in terms of PM 2.5, if you're not familiar exactly, these are very, very fine matters. And just to put this into perspective, these are particulate matters that are smaller than 2.5 micrometers. If you look at a piece of your own hair, we're talking about 1/30th in terms of diameter, 1/30th of the size of one hair. So really small, inhalable. They are very smart in terms of finding their ways easily into our lung system and into our body and penetrating there. The figure that you see right now on this slide, if you focus on particle pollutions, the green circles, you'll see that this can cause asthma attacks, lung cancer, wheezing, coughing, shortness of breath. There are all sorts of illnesses, but a lot of them associated with respiratory illnesses that are caused by or can be increased or affected by particle pollutions. Next slide, please. So why did we get interested to explore this relationship? And by this, I mean the relationship between PM 2.5 and, or VMT-induced PM 2.5 and COVID. If you look at the figure on the left-hand side, what it's showing you is the external cost of PM 2.5 in terms of dollar per ton. And when I talk about external costs, I mean the environmental damages, but also mortality and morbidity. So cost of mortality, morbidity of PM 2.5 based on dollar per ton. And when you look at that figure, you can see that the state of California, a couple other states in the West Coast are sort of categorized high. And then as we move towards the east, we see sort of the trend and, you know, everything gets sort of like more costly, again, in terms of health impacts of PM 2.5 as we go, as we get close to the East Coast. On the right-hand side, the figure that you are looking at shows you the geographical distribution of attributable burden of chronic kidney diseases resulting from PM 2.5. And you can kind of see from the high level that it follows the same pattern. You know, looking at these two, we were interested to see, okay, are we going to have the same kind of high level relationship first if we look at the COVID cases across the US over the past few months? If you click, please. Thank you. So, and surely enough, the diagram, the figure that you see on the left-hand side is showing you the confirmed coronavirus cases in the US. And again, you know, we're seeing, this is statewide, so it's not as disaggregated as the other two figures that I showed you, but you still see the same pattern. Again, you know, like more of heat, darker colors towards the East Coast, Arizona and California and so on. So this was sort of like, with everything that I've said, this was the motivation behind the study and how we got interested to explore this relationship and see what we can figure out. Next slide. Okay, so let me first tell you what the scientific world tells us about these relationships, what we know thus far. In terms of the relationship between viruses and PM 2.5, we know, or the scientific world tells us, that PM 2.5 boosts respiratory virus infection. We also know particles inhalation increases virus penetration into the deepest parts of their respiratory system. And a virus is a respiratory influential disease factor that has its synergistic effect together with PM 2.5. These are all from published articles in reputable journals. In terms of VMT and PM 2.5, we know that VMT is responsible for 10% of the total PM 2.5 in the US. We also know that incremental PM 2.5 decreases by 75% if we stand next to a freeway or 5 meters from the freeway versus 30 meters away from the freeway. So there's like a huge decrease as we get farther away from a given roadway. Also, average transportation air pollution costs across the US is 1.3 cents per VMT. So that's, again, what we know in terms of literature from the relationship between PM 2.5 and VMT. In terms of COVID, research shows that COVID-19 could be airborne. We realize that there is some disagreement on this, but again, most everything that's been published up to date is supporting this, this sentence that COVID-19 is in fact airborne. PM 2.5 can act as a transmitter agent for many viruses, as I mentioned a little earlier. Next slide, please. So let me turn it over to Hojat, and he will continue telling you about the analysis.
Thank you, Professor, and good morning. Okay, about the data sources, in terms of the data sources, we used Johns Hopkins repository to obtain COVID-19 daily new cases. On the figure, the blue line shows the daily new confirmed cases, and the orange one shows the number of the deaths. PM2.5 daily concentration levels are obtained from the EPA data centers, and the 2070 VMT data are collected from the FHWA data center. For geographical basis, combined statistical areas selected as they are the most homogeneous socioeconomical boundaries in the United States, and the PM2.5, COVID-19, and the VMT data were aggregated to their CSA geographical level. The study period is from March 15th until August 17th of this year. So the study includes 145 days and 149 CSA, as you can see in the table. And the CSA are the most densely populated area in the United States. They have 78% of the US population, while only cover 24% of US land area. To conduct correlation analysis using a Spearman correlation for nonlinear relationship and 10 days moving average technique, we evaluate correlation between PM2.5 and the COVID-19 for entire 145 days. We also evaluated short-term correlation using the sliding window technique. And lastly, we looked into the relationship between VMT on PM2.5 concentration in given areas. Okay, here are results. For the first part, the correlation analysis for the entire 145 days, no significant pattern or correlation was found. This perhaps explained by the fact that any short-term weather changes like wind can temporarily change PM2.5 concentration levels, or a local curfew in a specific area can temporarily reduce the number of COVID-19 new cases. And these temporary short-term changes affect the correlation factor seriously. For the short-term correlation, we set a threshold of correlation factor being at least 0.8 and the p-value of less than 0.05. This represents a solid correlation. We explored significant correlation for periods greater than 2 weeks. This provides confidence that this short-term correlation is not random. The result indicates that 143 CSA had at least one strong correlated short-term periods of more than 40 days, as you can see in the table. This is 96% of the total CSA, and the average length of these shorter correlated period was 44 days. Here. This table here shows 10 CSA that have the most prolonged correlated periods. It also includes 2 CSA with a 145 days correlation period, which is the entire study period. At the bottom, you see a histogram showing the distribution of the CSA for the varying period length beams. The y-axis on the left show the number of the CSA, the y-axis on the right show the percent of the CSA, and for example, 46 CSA have correlated periods between 14 and 35 days. Here. This graph explains the number of the CSA with correlated periods for each day of the entire study period. The y-axis showing the average PM2.5 concentration, and the y-axis on the right is showing the number of CSA. For example, on the 20th of March, 19 CSA have correlated short-term periods on that specific day, or on the 2nd of July, 93 CSA have correlated short-term periods. This figure reveals another special relationship. The brown line shows the average daily PM2.5 concentration level in all CSA for each day. It indicates that as the average PM2.5 concentration level increased from 6.5 to 8 during the beginning of July, more CSA shows correlation. This concentration level soon declined to 6.3, as you can see, and consequently, the number of correlated CSAs decreased accordingly. This presents a potential confirmation that the PM2.5 concentration level affect the correlation between the PM2.5 and the number of the COVID-19 new cases in this study. Oh, sorry. And this figure, the correlation between VMT and new produced measure PM2.5 land area is presented for each CSA here in this figure. We know that the PM2.5 concentration level is a density measure, and production of that with land area gives an indicator for the amount of the PM2.5 in that specific area. These two measures show a robust correlation with correlation factor of 0.78 and p-value 4.2 e minus 20. Also, the figure shows a nonlinear logarithmic relationship between VMT and the amount of the PM2.5. This presents a solid relationship between the amount of the PM2.5 and the VMT at the designated area. Here you are, Professor.
Thank you, Hojat. So this is also interesting. We wanted to bring it to your attention. The top table that you're seeing here on the left-hand side, you see a list of 10 CSAs. And this is from an internal research that we have done that is now published. It shows the CSAs with the largest VMT-induced pollution emission across the U.S. So what you see again, top 10 highest polluted CSAs, not any pollution induced by surface transportation. And then on the right-hand side of that table, you see the associated VMT. I apologize, I just noticed that the title has a little bit of typo. It's the total VMT, it's not per 1 million population. The table at the bottom, interestingly, shows you the confirmed cases of COVID and like the highest COVID infection totals. Again, it's not a rate; it's not per 1 million population. I apologize for that. For a number of CSAs with the highest cases. And you will see a lot of, if not all, a lot of those CSAs are being repeated. That you see the same names at the bottom table, not exactly in the same order, but I thought this would be also interesting to point out. Next slide, please. Okay, so this is what I want to emphasize here. We all know correlation does not imply causation. That's pretty clear. That should be a clear message here. COVID-19 potential risk factors, as we know, could be age, race, ethnicity, gender, medical condition, poverty. The list goes on and on. All we're saying is that PM2.5 exposure could also be another risk factor. As we've talked about already, PM2.5 can act as a facilitator for viral transmission. It's not only COVID. For any virus, PM2.5 can act as a transmitter. We also want to sort of point out, and this is, I think, important within the context, people living in areas with high concentration of PM2.5 may already be at higher risk due to long-term exposure to PM2.5. But all in all, from this study, we saw a significant positive relationship between PM2.5 concentration and VMT, as well as COVID-19 daily cases and the PM2.5 concentration level. Next slide, please. So what does this mean to us as the transportation community? First and foremost, efforts to decrease urban driving will have important impacts on mortality and morbidity rates. So it's not only climate change. Climate change is obviously very important, but we got to be concerned about mortality and morbidity rate, health impacts, and so on as well. The transportation sector must play a major role in lowering PM2.5 concentration level. Mobility and safety, accessibility, performance measures must include air pollution safety criteria. It is important. Again, I know that we have been paying attention. We as the community, we have been paying attention to emissions over the last couple decades. But again, most of that has been focused on climate change. That is great, but we got to add the health and safety impacts to that as well. Lastly, air pollution safety criteria guidelines must be provided to local transportation authorities, especially in those areas with higher air pollution. So I think that's sort of like the message for this. In terms of going forward, we are not done with this study. Exploring the impacts and interactions of other factors, obviously very important here. We are looking at epidemiology factors. If you look behind me, you may see that I'm already looking at some radiographs in terms of demographics and what has been done over the last, or who has been affected over the last few months. Climatology is important. The way wind comes and goes, affecting the concentration level of PM 2.5 matters, and we're going to explore those. Exploring real-time daily VMT and its effect on PM 2.5 is very important. Unfortunately, finding real-time daily VMT is not as easy. If any of you or any organization could help us with that, near real-time or real-time daily VMT, we would like to have that and use it. That would be really amazing for this project. Ultimately, what we want to do is using AI techniques for predictive modeling to do daily VMT to explore more of this relationship. Thank you so much for your attention. It was an honor, and we are here to answer questions if you have time.
Okay, we do have a couple of questions here. The first one is they were wondering what was the date of the data that was used, because they were wondering that some of the pale states are now showing as spikes, and they were wondering, wouldn't it be a better way to track COVID data in a case per total population?
I believe we did look at data, the rate per population. As you saw in one of my tables, I even had those numbers on, but then I decided to change them last minute, and I forgot to change the title. Hojat, do you want to talk a little bit about the dates for COVID cases that we used? I believe it's at the end of August.
Yeah, the end of August was the final day, and it was starting from the 15th of the March until the end of the August. Because of that, you cannot see the spike of the nowadays it spikes.
Okay.
So all in all, let me just, sorry, Dave. So we are looking at all sorts of rates. It's not, what we are showing here is just a synopsis of everything that we have done. But if you are interested, please let us know, and we are happy to share all sorts of different interesting relationships and patterns that we have figured out thus far.
The next question is, during quarantine period, VMT reduced dramatically, but not COVID-19 cases. How was COVID-19 cases related to VMT?
So this is the part that this is a great question, and this relates to my plea at the end of the presentation to help us out if you have access to real-time or near real-time VMT. Unfortunately, it's hard. Finding daily PM 2.5 is easy. It's accessible. COVID cases based on at least John Hopkins database is accessible. And maybe this is something, again, as a transportation community, we need to work on. Finding daily VMT or real-time VMT, even near real-time VMT is not an easy task. The most reliable set of data that we could find, as you saw, goes back to 2017. We would love to have real-time data and sort of see how exactly on a daily basis we went up and down with people doing less of driving, significantly less of driving in these areas during the months of April, May, March. And then peaking up again now. So we would like to see that. Unfortunately, we couldn't go into as much details as we would have hoped for with VMT data. But we see the point. We see how that could impact everything. Yes, we have talked with NRIX, and we are discussing things with them. So hopefully something good will come out of that. Thank you.
your study made sense based on what is happening in India, especially in big cities with dense population. What month or year is being considered so that COVID-19 cases are significantly dropped, if you know that answer?
Well, Jad, do we know the answer specifically to that?
Oh, for sure. Only we thinking that the PM 2.5 concentration level has a relationship with the number of the new daily new cases, and as a suggestion, we can suggest that if the PM 2.5 can be a gadget that shows that if it goes up, it's very dangerous, and we can do more, we implement more policies that reduce the PM 2.5, and then after that we can think that these two relations, how can affect to each other. Then reducing the PM 2.5 concentration level is a policy that can help reducing the number of the COVID-19 new cases.
Do we know what months, based on our study, we went down? We could see from those figures.
Down of usually the PM 2.5 is higher compared to the other. I have it here. You can see 0.5 in the colder season, and we can easily forecast that this winter will be the higher PM 2.5 concentration level compared to the summertime, and because of that, we are worried about that maybe this can affect the number of the cases, and this is it can be a factor also.
So the seasonal, the seasons matter. I guess that's what Hojat is alluding to. We are seeing the spike now. Part of it could be due to many factors, but the recent spike that we are seeing could also be due to the colder season and the fact that PM 2.5 concentration level goes up during the winter time. Density is always related to both VMT, PM 2.5, and I'm suspecting to also the COVID cases. So that is not something, that's why we were interested to begin with on rates per population. So I see a lot of questions are coming up in terms of sort of like for the international world. It would be, this study was focused only on major CSAs in the US. It would be really interesting to see if hopefully soon we're going to have that predictive model using machine learning techniques. And it would be really interesting to test that and see how it works in places like India, Latin America, Middle East, even where things are really bad. So we're looking forward to that.
Okay, thank you, Yagana and Hojat. That was a very interesting presentation. Our third presentation this morning is Behavior of Concrete Barriers for Bridges in New Jersey, presented by Dr. Anil Agarwal of the City College of New York.
Thank you very much. All right, so thank you for the kind introduction. Topic of my presentation is behavior of concrete barriers for bridges in New Jersey. The work has been done in partnership with my collaborator, Dr. Saif Al-Tawil at University of Michigan. Dr. Ran Kao, who was my graduate student, he's back in China at Hunan University. And with Dr. Hani Nassif and He Jiang at Rutgers University. Part of this work was done part of Federal Highway contract we had on hazard mitigation team with Mr. Vairavang from Federal Highway Resource Center, and also through sponsorship from New Jersey DOT in collaboration with Dr. Hani Nassif. So we sincerely appreciate the support and feedback by Ali Nazam and Anna Cheng from New Jersey NJDOT BRP. Going to the objective, this was a very broad study we had from Federal Highway on, behavior of different kind of barriers, and so we'll talk about part of. So the research is very broad, so I will only go through the key outcomes and key results for different kind of barriers, TL4, TL5, and TL6 concrete barriers during the last 4 years. Particularly, we'll talk about the demand model, which is not available till now, but we have developed new kind of demand models which can be used for a simple design office to design these barriers instead of requiring complex analysis or testing, and also a performance approach how to design it. And also, we'll talk about the behavior of FSF New Jersey duty barriers through numerical simulations. If you look at about the TL4 barriers, which are medium weight truck hitting bridge barriers. So current TTI recommendation is actually this table show you what TTI recommends for these barriers. So generally TTI recommended 80 kips as the average static force for railing design. In current ASTO, it's 54 kips. It's a recommended new one is 80 kips. When we started doing this work, Federal Highway asked us to look at current approach and see if there's something which can be improved, or we can do design approach so that people can design these barriers more simply. And the eventual goal is that each of these barriers, when designed, they needed to be tested, crash testing. So idea is to develop reliable design models so we can avoid a very expensive crash testing and just based on a simple design approach. So when we started looking at TTI's work, we found that all these forces that you see, 80 kips force per TL4 barrier, they are based on modeling the barriers as rigid. So the rigid barrier assumption. So when you have something very rigid like a steel wall and you crash against it, the force will be much higher compared to if you think concrete, which is still deformable, it is still damageable. So force should be lesser than that. So there's a dynamic effect, which is because the material behavior, which is not incorporated in these forces. And also they wanted independent verification of simulation results. The third thing is that current ASTO LRFD approach for the capacity estimation. So one part is demand, but then capacity estimation is other part. So the current approach for capacity estimation is based on yield line approach, which heavily underestimates the actual barrier capacity. So we have developed a new approach for the capacity estimation. So going to the TL4 barrier, so this will be a TL4 typical TL4 barrier where a medium weight truck, a single unit truck will hit against the barrier, and this is the barrier in our model where you have this this barrier, and this work we are doing in Elastano. So this is the barrier where the truck will go and impact, and then we'll see the behavior of the barrier. Reliability of the simulation is always very important. We want to make sure that our results are as accurate as possible and represent the actual scenario. So we take a testing from TTI. This is the top figure that you see. It's actual crash testing where the truck model comes and hits the barrier, and these are the different steps of the impact. And we do the simulation with this model of the single unit truck that we have from Federal Highway, and we model this barrier, and with this barrier, we impact the truck into the barrier. And you can see that this, crash testing in our numerical model is almost identical to what we see from the TTI testing. So for the TL4 barrier, the current ASTO code says 54 kips design load. The new recommended load for TTI from TTI is this is a Texas Transportation Institute, which has done measure the work in this area, is 80 kips as average static force per railing design. When Federal Highway asked us to initially look into the issue of barriers, we found that currently TTI barriers are designed by assuming barrier is rigid, like a steel wall. In reality, the barrier is made of concrete. It gets damaged, gets deformed. So when the deformable barrier will have a lot less force than what you have the rigid barrier. Federal Highway also wanted an independent verification of simulation results. And then what we noticed was that they use a yield line approach, and which may actually underestimate the actual barrier capacity. So we are using a demand model. We actually developed a demand model which can actually better estimate the capacity of the barrier. So this is our tier 4 barrier. Single unit track is impacting a barrier. And this is a single unit track which has been designed by, this is a model in LSDANA, which has been designed by Federal Highway. It's available from Federal Highway website, crash testing website. So the reliability of the results is very important. So what we do is, to make sure that our results are reliable, we, take a testing from TTI. This is the TTI testing, which is, you can see this actual crash testing, and then we model this actual crash testing in the barrier. And you can see that, visually the results are almost similar, that, actual crash testing matches very well with what we have in our simulation. But further, we look at the force, forces and, deformations and acceleration. So you can look at the lateral acceleration. So this acceleration that of the track at the center of gravity during the impact. And, simulation is red line, test is dotted black line. And you can see that matching is fairly good, given this kinds of complex simulation with the track is hitting a barrier. And again, we can look at the damage model TL4 barrier. This is the blue one that you see the actual impact. You can see this damage to the barrier. And these are the tire marks when the tire hits the barrier. That these are, again, very similar to what, we have from the actual testing that we get from the simulation. So this gives actually very good confidence that, what we are doing in the simulation actually represents the actual phenomena. So based on the result, then what we want to do is we want to develop a demand model. Means every time that you want to do a design, you don't want to do actual crash testing like this, or you don't want to do actual simulation, LSDANA, the complex simulation. Rather, we want to do the similar design in the design office, and that can simplify the work a lot. So what we do is this simulation that you see here, the track impacting the barrier. We do a lot of simulation of this for, many different velocities of the truck and many different weights of the truck from 8.8 ton to 30.2 ton. So once we have these weights and, the force time history, every time the truck hits the barrier, we also monitor how much is the force, impact force. So this is, you are seeing is the force time history. And we simulate this for different barrier heights, different barrier weights, okay? And then we go into the regression model. We select a form of the equation where the peak force, we are looking at the peak force of this, impact time history. And we define this peak force as a function of some constant times v to the power 1 exponent and weight to the power exponent. Because it's understood and we know from the past research that the peak impact force will be a function of velocity and weight of the truck. So based on the regression results, we have 15 cases. For 15 cases, we get all this data and do the regression to find this equation that you are seeing, Africa 2.30, v to the power 1.24, weight to the power 0.41. So this equation now actually can be used to find the peak impact force acting on the barrier. So once we have this demand model, then we want to see how we want to use this demand model for the design. So what we do is we do based on all the simulation results that we have. We start, we take the lateral displacement versus demand capacity data, and using this lateral displacement versus demand capacity data. So lateral displacement is the displacement of the barrier. And the demand versus capacity ratio is what we calculate. D is the dynamic impact force, which is based on this equation we have. So in this plot, what you see is D is the dynamic impact force, which is based on a demand model. And then C is the barrier capacity. And we calculate this barrier capacity based on the rebar detailing. And if you plot this lateral displacement versus the demand capacity ratio, and what you see is very interesting thing that, these are the dots that you see are for, different demand capacities. That there's a zone where you have no damage, there's a zone where you have minor damage, and the minor damage is basically function of this damage is function of lateral displacement. And there's a zone where you have actually heavy damage, but then the criteria for the barriers is to redirect the truck. So in this major damage, it's a near collapse, but the barrier has fully developed yielding, but it still redirects the truck, which is the objective of barriers, that it will, make sure the truck is redirected back to the traffic. So you can see that, based on this simulation, that we can find very clearly defined zones of demand and capacity ratio. No damage, minor damage, and a fully developed area. And this table shows you that you have no damage where demand capacity between 0.0 to 0.6, and maximum displacement will be around 0.1 inch. You have a minor control, what you call it minor damage, we call damage control. You have 0.6 to 1. And the displacement in the range of 0.1 to 0.5. And then you have the near collapse, a fully damaged barrier, which will need to be replaced eventually after accident. It's, the demand capacity between 1 to 1.5. And you have a displacement in the range of 0.5 to 2 inch. So this is now an approach that we can use. So, for example, next time you want to design a barrier, all you have to do is, instead of doing all the complicated truck simulation, all you have to do is go and find the weight of the truck and the velocity of the truck. You find the demand, okay? Now, you can decide where you want to be. If you know the demand, you can decide where you want to be, no damage, minor damage, or, or near collapse. For example, let's say you want to be in the zone somewhere like at the boundary of minor damage and near collapse. So you select demand capacity ratio equal to 1. So if you have a demand capacity ratio equal to 1, so from this chart, because you already know the demand, so if your capacity is 1, that if your DC ratio is 1, that means your capacity will be the same as demand. So now you know the capacity. So all you have to do is go to the design code, and for that capacity, you do the rebar detailing to get your barrier design. So your design becomes a lot more simpler. In fact, it's a simple design office calculation which can be done in a matter of a couple of hours. But we also want to see whether how reliable is this approach. So what we do is we start taking some example and some verification cases. So we take one example, which is the mass TL4 truck. Weight is 11 tons, velocity is 56 miles per hour. And if you follow that equation that we have demand model, then you get 118 kips, okay? Now let's say you want to design a barrier with a minor damage. So your DC will be 0.6 to 1, right? So you have minor damage, you have 0.6 to 1. So if you take the limit of 0.6, then your required capacity is 196. If it is a limit 1, then your capacity will be 118. So your capacity will vary between 118 to 196. We designed a barrier, and we found that our actual capacity was 125 based on the design. And actual, so we in our example we took 1 as our desired DC ratio. And we designed a barrier for DC ratio 1. So we got we designed for 118 kips capacity. When we do the pushover analysis, which is very reliable, we find the barrier has 125 kips capacity. Actual DC ratio is 0.94, which is close to 1 that we assumed. So we are somewhere between 0.6 to 0.1. We wanted a DC ratio of 1. We got around 0.94. With the crash testing, we did the simulation of the barrier. And when we did the simulation of the barrier, we found the actual deformation was 0.3 inch. Now for 100, for this barrier, for minor damage, our displacement range was in the 0.1 to 0.5. So we are right in the zone of 0.3 inch. So this was the approach that we have actually, that you are going to design the barrier. It's really, pretty good. We can actually get the performance that we are designing for. So that's actually a pretty good, thing that now we don't have to do complex simulation. In fact, this is the amount of calculation that you do to design a barrier. You find the capacity and then you design for the capacity. That's it. So simple concrete design, and you could design a barrier. Now going to TL5 barrier. TL5 barriers are where they're impacted by tractor semi-trailer. So in our simulation again, what we do is we have a model for this trailer that I'll talk about. And when this track goes and hit the tractor semi-trailer goes and hits a barrier, this is a 42-inch barrier, and we have this model, and we set it up so that it will go and the front of the truck will hit the barrier, and then eventually the rear wheels will go and hit the barrier. So for this kind of impact, there are three major events. The first, the impact of the bumper and the front tractor wheel. The barriers will go and, the bumpers and front tractor will go and hit the barrier. And after that, impact of the rear tractor tandem axles will hit. And eventually what will happen is impact of the rear wheels, rear tractor will on the barrier. And this is called the slap back effect. And generally, this is the most, severe of all the three events that control the behavior of the barrier during this TL5 truck impacts. Again, I'm not going into a lot of detail, but what we do is for this truck also, we carry out a lot of simulations for this. We have many cases, I think around 18 or 20 cases. Each of those cases actually takes us a couple of days of simulation in one of the fastest computers we have. And for each of the cases, we actually do the impact force time history. And once we have the impact force time history, now this is specific to a truck or a weight or velocity. So what we do is we vary the velocity of the truck, vary the weight of the truck, and we also in this case vary the barrier height from 42 to 48 to 54 inch. And then we get the this impact force time history for each of these cases. Now it's very difficult to represent these three ones, but like I told you earlier, that out of all these three events, this slapback effect is the most serious one. So we develop a dynamic model in this case, which is this circle, this impact area that you are, impact force time history that you are seeing. We simplify it by a triangular pulse, this triangular pulse, okay? And the peak force for different cases we take, and we do the regression analysis to find this equation, just like for the TL4 barrier that I showed you, that we find the regression equation, the parameters of these regressions. So now we have the peak force. We also find the duration of this pulse based on the simulation. And once we have this, so you can see here that, it's around 0.2 or something. So we have actually the width of the pulse is 0.2. Now, when you're going to design a barrier, typically what we'll do is for this barrier height H, this force, this triangular force will be applied into this area D over LT. And from the simulation, we have found this D over LT for different barriers. So this is a pulse model. This is a dynamic model in this case. So once you take this pulse model, in a simple design office, you can model a barrier, apply this force, and you can do the time history analysis to find the impact force and displacement and all those things that you need for the design. That is, again, it's a lot more simpler than actually doing this simulation, which, developing the model and everything. It actually takes several months of the work to do this kind of simulation. If you have to do in real practice, and a lot of time, the DOTs actually have to do this work, this simulation, to find the behavior of the barrier. Instead of that, you can do this, which you can still do in a matter of 1 day or so, get all the results. So how good is this model? First of all, let's look at the time history. In this time history, what you have is, this is the truck simulation, the black curve, and the red one is the pulse simulation. And you can see there's an excellent matching between the two. our interest is actually going up to the peak here. And beyond that, this is just the vibration. So we are not really worried about. We're worried about how good are these in terms of getting the peak force. And we can say almost very similar, the truck simulation pulse model. So it's really amazing that such a complex process you have of impacting and getting all these forces, the complex impact process between the truck and the barrier, you can actually simplify with such a simple, model that you can use for the design. You can see here the truck simulation, pulse simulation, you can see the damage to the barrier. And here actually, this is more clear. This is the truck simulation, the front view, and this is the pulse simulation front view. You can see the damage to the barrier. The behavior is almost very similar. So that shows that this model is again very good and can be used to design TL5 barrier. Of course, in the future with Federal Highway and other agencies, we are planning to see if we can verify this model with more truck simulation. But right now, because our truck model has been well calibrated, we have very good, a very high degree of confidence that this is going to work for all kinds of simulation for the TL5 truck. Again, to design the barriers for TL5 truck, we have developed a performance approach. If you assume this is the barrier and you apply a force here, this barrier will deform by a displacement delta. Okay, so you could define an angle alpha equal to delta over h. And then what we do is, in this case, we define different performance levels. We have only two. All these simulation results we have, we take all the simulation results and we plot the rotation, this rotation that you see. We plot the rotation as a function of d over c. And what we see is the rotation of function of d over c. We can see the clearly identified zones for different barrier heights. You have this zone where you have minor damage, the displacement is less than 0.01, the rotation is less than 0.01 radian. And then you have the zone where the simulation shows that you have a yield mechanism, the rebars have yielded, but the barrier is still able to redirect the truck. This is the requirement on the barrier. So you can see that we have this performance curve, and we can use this performance curve to design the barrier. So how good is this model? Again, we can look at three types of barrier: 42 inch, 48 inch, 34 inch, and these are the ASTO forces required right now. ASTO guideline gives you 124 fixed force for all the barrier. But the current guideline from TTI, they propose this force which is 159 kFs, 261 and 295 for three different barriers. If you go now dynamic pulse model, because you already take care of the dynamic behavior, then we say that these are the force level which are much level than what you have the static force demand. So our dynamic force demand is much lesser than the static force demand that we have. Also, we look at the design of the barrier, that how good the design of the barrier could be. So this is the ASTO approach. If you design a barrier with the ASTO approach, you have this anchor bar, you have this anchor rebar and wall thickness detailing that the wall thickness will be 12 inch, and number 5 rebar at 7 inch spacing. So you have a lot of rebar there. If you use a new TTI recommendation, that's going to be in force. Demand is 296 gauge. You have number 5 at even more rebar. Number 5 at 4 inch spacing, and 17 is thick barrier now. And in these two cases, you have yield mechanism, but it redirects the truck. The TTI, the damage is less, but you have the very massive amount of force. Okay, if we follow our approach, and if you want to design similar one, so if you take 191 kFs force and follow our approach, you can see we actually require number 5 rebar at 10 inch spacing. So compared to this case, ASTO case now, we have actually a lot lesser, only 10 inch and only 12 inch thick barrier, the same 12 inch thick barrier, but the rebar detailing a lot less. Still, we have a yield mechanism forming, it will redirect that. But if you want to design at better performance level that you don't want any damage, then your barrier will be 15 inch thick compared to 7 inch thick by the current recommendation TTI, and the rebar detailing will be half, number 5 at 8 inch spacing. Instead of what is coming from TTI, number 5 at 4 inch spacing. So our our approach is certainly able to, minimize, economize the design drastically, while it's also telling you what is your performance. In the current Aston TTI, they do not tell you what is your predicted performance. In our model, it will tell you precisely what kind of performance you are going to get. And then finally, TL6 barrier, where, in the TL6 barrier, the truck is actually tanker truck. So right now, there is no model existing for the TL6 truck. So what we did was our truck model, we modified, removed the, this trailer and changed the trailer to a tanker. And then we go and do the simulation, which one of the tests which was done in 1989, crash against estimated wall by TTI. And in this plot that you see, this dark line is actually impact, the testing. And the blue line is actually our simulation. And there's a difference between there's a difference in time between the two plots, which is actually because of the different length of the trailer bed. But you can see the peak forces, peak demand in all three cases are almost the same. Now, if you look at the impact mechanism here, that the first, this you see here, this is impact from the tractor wheels and bumper. And then you have the impact from the tanker and the tractor rear wheels. The tanker goes hit and tractor wheels go in. And then the third one, which is most severe one, is the impact from the tanker and the trailer wheel. And that's what causes the maximum damage. So following the similar approach that we had, we, like I showed you, we have these three impact event, and these are the 3 force time history. And this is the most severe one. So what we do is, and we also try to find in this case, because unlike other truck model, now I have the tanker also which is hitting the barrier beside the tire. So we also find from our simulation what is the best location for the force to be applied, both in the vertical direction, in the horizontal direction. And based on this, all these simulations, we go and form our model again. This is our pulse model again, similar to TL5 barrier. Only thing is its parameters are different. This is the force that will be applied in the actual barrier in the design. This is the transfer phase of the barrier. You can build this model in any of the software like SAP 2000, any commercial software. So 100 inch by 20 inch, and we developed this regression model based on, again, a lot of simulation data. You can see the comparison between the actual truck simulation and pulse simulation. But the comparison is really very good between, if you look at the displacement, which is the indicator of the damage, then we get actually displacement pretty close to what we have from the truck simulation. Given that this simulation process is again very complex, that one set of simulation takes us several days in our fastest computer, and developing this simulation, if you want to do for the barrier design, it really thinks that it will really take several months to do the simulation. So we can design a simple barrier with apply this pulse. This is a dynamic pulse that you apply as a pressure in this area. Do the simulation. From this, you can find the demand. So when we go to the performance approach, we have similar kind of performance approach for this. Just like this, I showed you. We have a performance approach just like this, where you can calculate the demand, find the capacity, and based on the capacity, you can design the barrier. Just to avoid repetition, I did not show you the work. So going to the last part of our simulation, the next part, the yield line method for estimating capacity. I have 2 slides that I want to show you quickly. The current AS2 method does capacity estimation based on the B shape during the impact. What we do is we go and look at the pushover analysis, which is done earthquake engineering, and tries to see if this B shape is really good or not. So we go and create a model in LS-DYNA. We apply the loading here, do the pushover analysis. This is the loading area. And when we do the pushover analysis, when we do the pushover analysis, this is what we say, that for that barrier, this is your capacity. The capacity is really very high. This is the ASTO based on the B shape that underestimate the capacity more than 20%. So what we do a lot of simulation, and based on the simulation, what we observe is that when the truck hits the barrier, okay, the damage mode is actually not the V shape. It's kind of like a W shape. So this W shape barrier, we can go and recalculate the capacity for the W shape barrier. And then if you see a W shape, this is our new model. This is the W shape model, this is the base shape model. So our W shape model can actually give you much better representation of the capacity compared to ASTO. What is happening is you are actually assuming based on ASTO, this is the capacity, actual capacity, this one. So all this range of the capacity is actually waste because you're over designing and not knowing that you're over designing. So our model for the capacity estimation is again much better and gives you much better estimation of the capacity for the barrier. But some of this work we have already had a discussion with the ASTO. Some of the work that we are presenting, it may actually very soon go in the ASTO barrier. Now this W shape is not actually new. No, we have been doing experiment and we have been doing from a lot of the experiment. All right, so this model is pretty good. So if we do the B-shape model, I'm not going to do the design, but when you do the bridge or railing overhang, what we see is that it could reduce the design, the detailing, rebar detailing by 23% or 30%. It would come at a significant, economy. The last part is New Jersey crash simulation of the barrier. Idea is again to look at the finite element simulation, develop the performance of the precast mass TL5 barrier, and provide design recommendation to TL5 barrier. So this is the barrier that New Jersey DOT was planning to use. We have this open expansion joint at every 20 feet and 10 feet panels here. This is the barrier point we have. We go and do the simulation. For the simulation, we do the calibration using testing data. We do further testing data from what we have done the work in the past, and we see that simulation and it's matching very well. And then we go and develop a finite element model of the barrier, simulate with the truck impact, and try to see how is the barrier behavior with the barrier. So just one video showing this is from the front view, and this is from the rear view. You can see this barrier, the truck goes and hits the barrier. And what really happens, what we see is that the rear wheel, when the rear wheel hit, which is expected, that the barrier is deformed, and it's actually deforming quite a lot, 1.5 inch. And further, when you see the back slap effect, which is the rear wheel hitting, you can see the damage mode of the concrete, and you can see the rebars are yielding. One of the primary reasons the rebars are yielding is because of the and you can see you have the open joint when we impact on the open joint versus when the rear wheel are hitting one panel versus hitting two panel at the open joint. So the problem is it's more severe when the rear wheels are hitting one panel because the panel gets displaced and there's an impact at the offset between the two panels. So we go and try to put interlock between the panels, and when you put the interlock, the design actually gets much better. You have with the interlock, the design is safe. You have no deformation, you have no yielding, and the deformation is a lot less than 0.8 inch. So that gives a very good confidence that this barrier with the interlock and with the DOT can use, and it will not get damaged, and it will give you a very good performance during actual crash event. So with that, sorry, we had a lot of audio issues, but let me finish my presentation. Based on simulation, we have proposed TL5 for the New Jersey DOT part only. I'm summarizing. TL5 barrier can redact the colliding trailer track under mass condition. The peak impact force is around 220 kPa dynamic, which is consistent with what result I showed you earlier. The barrier didn't form, but had a permanent deformation of 1.5 inch. But if you add a shear interlock between the segments, it could improve the overall impact performance. And it could help in reducing the frequency of replacing the failed segment due to concerning impact. That's all I have. Thank you very much.
Okay, thank you, Dr. Agarwal. Unfortunately, we do not have time for questions. We're running slightly behind. Our next presentation is Accelerating Mobility for All. Analysis of focus group feedback from persons with disabilities following autonomous vehicle rides. Presented by Dr. Cecilia Feely and Andrea Lubin of Rutgers University.
Good morning, everyone. My name is Cecilia Feely, and I'm the Transportation Autism Project Manager at the Center for Advanced Infrastructure and Transportation at Rutgers University. I will be presenting today with my colleague, Andrea Lubin, who is a senior researcher at Voorhees Transportation Center, also at Rutgers. Both Andrea and I have focused much of our research, both independently and jointly, over the past 15 years on exploring transportation and mobility issues for persons with disabilities. We truly appreciate the opportunity to present some of our research with you today at the 22nd Annual NJDOT Research Showcase. Specifically, we will be sharing the highlights from focus group work conducted in spring 2019 to gather important feedback from persons with disabilities in New Jersey related to the direct experience in riding an autonomous vehicle shuttle. Our work was funded by CATE, University Transportation Center Region 2 UTC Consortium, and the USDOT Office of the Assistant Secretary for Research and Technology. This research was undertaken as a collaborative initiative between Rutgers and Princeton universities, with our Rutgers team comprised of myself, Andrea Lubin, and our colleague from CATE, Brian Tobin. Dr. Alan Kornhauser, Professor of Operations Research and Financial Engineering, was our Princeton University partner. I would also like to mention that our team also had the pleasure of collaborating with Janu Kwang from Texas A&M University, who supported our focus group sessions. So to begin, our project objective was to contribute to the limited body of research on designing and deploying autonomous vehicles, or AV, to accommodate the research needs of persons with disabilities. To achieve our objective, we convened a series of 4 focus group sessions to capture feedback from adults with visual impairments or developmental disabilities who experienced an autonomous shuttle ride. So why focus on AV? Well, as we are all aware, access to transportation is essential for anyone to become fully integrated into society. For persons with disability who are recognized as transportation disadvantaged population, relying on public transit and other non-driving options can be necessary to achieve inclusion and to meet trip needs. Non-driving options are essential for persons whose disability precludes them from operating a vehicle, even with current vehicle accessibility modifications that are available on the market. It is very likely that in the near future, the dynamic field of AV technology will be capable of offering a viable transportation option to transportation disadvantaged populations, including persons with disability, here in New Jersey and beyond. However, there has been a limited research focused on investigating strategies for designing and deploying AVs so they can best accommodate and be inclusive of persons living with one or more disabilities. I also want to point out that regarding innovation and adoption in the US, both the USDOT and the National Highway Traffic Safety Administration have been supportive of AV technology and development. While federal legislation on AV remains absent, many states are moving forward in exploring and adopting AV-related legislation and policies, with more than 30 having enacted some type of AV legislation. In 2019, New Jersey established a task force to study autonomous vehicles. Regarding our study methodology, we convened 4 focus group sessions during a 2-day period with a total of 21 adult participants with developmental disabilities or visual impairments. The sessions were held on the Princeton University campus immediately following a brief ride to give participants in a Local Motors Ollie AV shuttle. The Ollie shuttle is a 3D printed autonomous electric vehicle that was made available to our research team for portions of the 2-day period during the Princeton University 2019 Smart Driving Car Summit. Study inclusion criteria. This was for adults with disabilities between the ages of 18 to 64 who were able to maneuver themselves in and out of the vehicle independently and had the ability to participate in a 1-hour focus group discussion. Regarding our study limitations, There are a few. One is that it was a relatively small sample size of participants, a total of 21. Another is that our participants reported being blind or visually impaired or living with a developmental disability such as autism. But none of the participants reported having any comorbidities, physical or other type, for getting in and out of the vehicle. Also, due to state legal restrictions and IRB constraints, the vehicle was limited to operating on the Princeton University campus football field instead of on the local roadways. And finally, due to the unique conditions of the testing environment, an operator was on board for all the trips. I want to share that the majority of the participants reported being aware of self-driving cars and autonomous vehicles before our event. However, most possessed an extremely limited information on the technology. Current transportation modes utilized by the participants varied and included fixed route public transit, ADA complementary paratransit, ride hailing such as taxi, Uber, and Lyft, school transportation, and one participant was able to drive. The travel mode reported by the vast majority of participants with developmental disabilities was being a passenger in a vehicle driven by a family or friend. So, who are our participants in terms of demographic characteristics? As you can see on this slide, the majority were male in the age range of 22 to 29, and they resided with their parents. There was racial diversity among our participants, with 19 identifying as white Hispanic and 14% as Asian. The sample also demonstrated a range in educational levels attained, and I want to note that all study participants were medically diagnosed with their disability. So now onto our findings. Following staff and participant self-introductions, 2 brief videos that introduced the technology, and both of them are available on YouTube, about autonomous vehicles were shown to the group. After the videos concluded, participants were guided outdoors where they were introduced to the vehicle and boarded for a group ride. Immediately following the ride, they went to a nearby classroom for a focus group discussion. Each session was co-moderated by Andrea or myself. Key questions and prompts focused on capturing information on the full experience the participants encountered on the AV, from their first exposure to entering the vehicle, to riding the vehicle, and finally to exiting the vehicle post-trip. Now, regarding the initial impressions of the AV shuttle, notably, the feedback communicated by all was overwhelmingly positive regarding the vehicle's appearance. Comments shared included, "It looks cool, it's amazing, it looks so futuristic." While a few shared they were slightly apprehensive for their first trip, the majority explained that the dominant sentiment they had when first seeing the AV was excitement for that trip. All participants who reported they experienced both entering and exiting the vehicle as smooth and easy. Participants who were visually impaired specifically remarked that they really appreciated that the step between the ground and the floor was low. They also added that the handrail on the step up was also very helpful for exiting and entering the vehicle. Now, regarding the participants' onboard experience, I want to note that each of the 4 in-vehicle trips and focus group sessions were audio and video recorded. At least one member of our research team was on board the vehicle for each of those 4 trips and confirmed the recorded observations that there was limited participant conversation occurring during these trips. Instead, the participants truly appeared to have their attention focused on their experience and their surroundings. Participant feedback on the trip itself was also very positive, with all indicating they enjoyed the short journey. Words frequently used to describe the trip experience included comfortable, smooth, quiet, slow. Several noted that they really appreciated the slow travel speed, and that helped them ease the safety concerns about the vehicles. We also specifically discussed the topic of onboard noises, as persons with developmental disabilities, including autism, often experience auditory sensitivities However, only one participant remarked on any onboard travel noise, with all the others sharing that the ride was pleasingly quiet. Other facets of the trip experience discussed by participants focused on positive feedback related to the vehicle's large windows, which they explained afforded substantial natural light on board, offered a clear view of the exterior surroundings, and made the vehicle feel very open, which they very much appreciated. Many participants also reported that they liked the vehicle included an onboard video monitoring screens. There was actually 2 that were visible to the passengers. The rear-facing monitor provided a 360-degree image of the vehicle surrounding, while the front-facing monitor showed a series of static images. Several noted that the presence of the onboard video monitoring screens made them feel more secure during the trip. Now I will turn it over to Andrea, who will share our study findings.
Thanks so much, Cecilia. So how did our participants feel about using AV moving forward? Notably, 17 of the 21 participants, the overwhelming majority, reported that they were interested in traveling again in an AV based on their positive trip encounter, and shared preference for AV over other modes, particularly if made available on demand. Commentary from the 17 participants interested in being a passenger again in an AV focused on the opinion that availability of an AV travel option would facilitate much needed travel freedom and increased independence, especially because so many participants discussed the challenges of being dependent on their family for transportation. Notably, several participants who were dependent on family for transportation discussed not only the personal limitations they experienced from this arrangement, but also highlighted the difficulties their respective family members encountered in providing transportation. Many of the participants communicated that availability and usage of AV would also help to decrease feelings of isolation, depression, and even what they described as jealousy that they often feel when they cannot access a ride to a desired or needed destination. In discussing AV in comparison to other modes that they currently utilize, participant support and preference for AV was clearly expressed. For example, the few participants who reported driving discussed that riding in an AV would be less stressful overall compared to driving themselves, especially when traveling in unfamiliar locales. Others noted they preferred AV travel to the community transit options and ADA complementary paratransit they have utilized, mainly because they envision AV as a more on-demand, user-friendly travel option. Focus group participants were also extremely eager to share the multitude of destinations and trip types that they would seek to access utilizing an autonomous vehicle. Common responses included employment trips, college or other continuing education opportunities, and daily living trips such as shopping. Several participants also mentioned they would use AV as a feeder to public transit. Notably, participants in each of the sessions were most excited to discuss the numerous social and recreational places of interest they would seek to access using AV, which included movie theaters and music concerts, bookstores, beaches, and parks. I want to point out that this overwhelming group interest and enthusiasm in detailing destinations that they would seek to access using an AV really highlights not only their interest in the travel opportunities potentially available via AV, but likely also reflects their current universe of limited transportation options. A final topic discussed related to participant interest in utilizing self-driving vehicles was desire and/or need for personal assistance as an AV passenger, with tasks including vehicle boarding and/or carrying packages. The majority reported that they do not typically utilize such assistance with their current modes and would not need or want such assistance when traveling on an AV, at least not in the long term, with several participants with developmental disability indicating, however, that they would like the option of a family member accompanying them on AV trips until they felt comfortable traveling independently on this new mode. In contrast, several participants with visual impairments shared that it would be helpful if assistance was always available to open and close vehicle doors, to provide guidance to available seats, and to help with passenger bags, and to secure wheelchairs and/or other mobility devices. Our focus group participants also shared a variety of specific concerns with self-driving vehicles, as well as recommendations, with core issues focused on the topics of accessibility, vehicle safety, communication interface, comfort and design, cost, and availability. Almost all participants stressed that AV should be designed fully accessible, facilitating usage among persons with diverse disabilities. For example, accessibility components, including the kneeling feature and wheelchair lifts, should be standard on AV shuttles and buses. Also, all AV, including personal vehicles, should have onboard audio capability and other multi-sensory supports to communicate vehicle arrival information and to provide guidance and information on safe boarding, seatbelt usage, and other vehicle-related details that could be helpful to passengers. Safety-related AV concerns were the most discussed issues among participants in each focus group session, and numerous recommendations to ensure optimum safety were suggested, including usage of onboard cameras to capture safety-related incidents, as well as audio and visual sensors that can assist the AV in identifying and responding appropriately to approaching emergency vehicles. There was substantial discussion on the safety implications of both external, such as a vehicular crash, as well as internal, such as an AV technology malfunction or a passenger becoming ill on board types of incidents. Participants expressed concern that if either type of incident occurred, they could be stranded without assistance. Recommendations to address this concern focused on presence of an onboard attendant with a valid driver's license and vehicle mechanical expertise if possible, so that he or she could at a minimum troubleshoot, if not resolve, any technical malfunctions and secure emergency personnel assistance if needed. Two other safety-related topics discussed included participant preference for a 3-point seatbelt configuration as opposed to a lap belt, and vehicle capability to maintain speed with the flow of traffic on all roadways. Also related to safety was a discussion on the vehicle communication interface. Participants shared many questions related to the AV interface, primarily focused on how passengers were supposed to indicate their desired destination and schedule their trip. They wanted to know if they would be able to do so using the GPS technology on their cellular smartphones, which most indicated would be ideal, or if they would instead need to indicate their destination upon boarding the vehicle. Several recommended that the onboard interface should permit passengers to access a call center to secure live operator assistance if needed, especially vital in the event of an emergency. Vehicle design was another area of concern where participants shared recommendations. Participants with visual impairments noted that several design features should be incorporated that would aid in promoting passenger safety and orientation in an AV shuttle, including utilization of contrast, texture, and color on any vehicle steps, installation of a handrail on the vehicle exterior near the entrance, and utilization of a non-slip finish on the vehicle step or steps and flooring. The importance of all vehicles being climate controlled to ensure passenger comfort in all seasons was also stressed, as was the importance of having adequate, comfortable seating. Finally, vehicle availability and cost factors were discussed as concerns. Regarding availability, participants emphasized that they were eager for AV to function as an on-demand transport mode similar to ride-hailing options, and that usage would not require advanced reservations. Also on the topic of availability, interestingly, many conveyed contradictory sentiments regarding a desire for widespread availability of AV shuttles, but preference to travel via AV alone, not sharing their ride with other passengers. Some even acknowledged this conflicting sentiment by indicating that while their preference is to travel alone, they understand they may have to share rides. Participant discussion on cost concerns assumed that they would be paying for passenger trips on an AV as opposed to purchasing an AV for personal use. Many noted that affordability is a paramount concern and would ultimately be a main determinant in their AV usage. The question of how costs and fares would compare to other on-demand transport modes, such as ride-hailing options offered by Lyft or Uber, was also mentioned. Still others questioned the likely fare payment mechanism and stressed that access would be expanded, including among the unbanked, if several payment methods were available to passengers, including cash, smart card, and payment via smartphone applications. So to conclude, this study was truly an exciting and inspiring undertaking for our research team, as we were able to capture valuable primary data from adults with disabilities on perceptions, concerns, and recommendations related to autonomous vehicles. And as many of us are aware, people with disabilities are a population whose transportation needs are too often not considered. Our findings demonstrate both the potential value of AV for transportation disadvantaged populations and strong interest in this technology among persons with disability. I want to point out that most feedback communicated during our sessions did not differ based on participant disability type, whether they had a developmental disability or a visual disability, with several exceptions I noted, such as regarding desire for personal assistance on board. Initial impressions related to the AV used were extremely positive, as was the feedback shared on the actual trip experience. Based on their positive trip encounter, almost all, 81%, expressed interest in using an AV in the future, explaining that an AV travel option would facilitate increased transportation independence and reduce isolation.
Thanks, Andrea. Concerns and recommendations related to autonomous vehicles expressed by participants focus primarily on vehicle accessibility to enhance access for all users, as well as safety, communication, design, cost, and availability factors. Regarding safety issues, I want to emphasize participants were concerned with safety events both internal and external to the vehicle, with many suggesting that onboard attendant and inclusion of a two-way onboard communication interface would be helpful in addressing many of these concerns. Most participants want AV to function as an on-demand transport mode, similar to ride-hailing options, but they expressed mixed opinions on ride shares, with many indicating their preference to travel alone. Looking ahead, it's clear that additional research must be performed with persons with diverse disabilities to ensure all the needs are met and documented and considered as AV technology continues to advance. Such research will contribute immensely to efforts ensuring this technology can offer a viable travel option for everyone. Thank you very much. And here's our contact information if you wish to reach out to us.
Thank you, Cecilia and Andrea, especially for addressing questions in the chat pod to save us a little bit of time. Appreciate that. Our next presentation is developing an evaluation of a real-time truck detection method using deep learning-based object recognition techniques for truck parking information systems. Presented by Dr. Jo Young Lee of New Jersey Institute of Technology.
Good morning, everyone. Thank you for having me with this great opportunity to present one of our ongoing research project. Today, I'm going to talk about a part of this ongoing project, which is about the pilot study for truck parking information system, collaborating with NJDOT. Primarily, I will focus on a methodology to detect truck by using computer vision technologies. Before getting into the detail, let me start from the background of this research first. Well, the ability to communicate truck parking availability to the truck drivers before they arrive at certain parking space is very critical, because this can directly impact the traffic safety, efficiency, especially for the grounding, the freight in transportation industry. So enabling truck drivers to know the availability of trucks parking spots help them reduce the unproductive truck travel and the overall vehicle miles traveled. It also able to improve truck drivers' compliance with the federal out of service regulations. So to advance the implementation of truck parking information system, which can help drivers conduct that kind of the informations available, NJDOT initiated a truck parking information system, or TPIS, pilot study at one of the each its truck parking facilities with NJIT ITS Resource Center. The specific objectives of the TPS pilot program is like to provide the foundations for a proof of concept and then pilot deployment of TPS to demonstrate whether the technology we adopt can accurately identify available parking space. And also, the parking information we can provide will be able to communicate the drivers in a timely, useful, and efficient manner. It also focuses on the demonstration of feasibility of the concept of the TPS in overall in a limited deployment, because we have some challenges in the spaces and facilities and the budgets as well. And then also, it also focuses on the development of this approach we propose can be scaled up and then replicate the same concept and the technology at the other parking facility in New Jersey. So with that, we briefly looked into the current truck parking status in New Jersey first. There are a total of 10 truck parking spaces in New Jersey, and then out of these 3,010, 808 spaces are public, and the rest of them is private. But both public and private parking spaces has a common issue, which is there's a large number of truck parking facility having some sort of the overutilization that causing some of the capacity issues. So almost all parking spaces we have in New Jersey has some sort of issue of the demand that exceeded the current capacity. As you can see on this the illustration on the right side of the slide. So that truck parking issue caused by this lack of available spaces are actually worsened by the congestions on a major New Jersey highway. For example, the George Washington bridges, is known as one of the top rate, the bottleneck area, just because of this the lack of available parking space in and around that Portland and the New York City. And then the truck parking around Newark Industrial Zone was identified by the NJTPA that there are over 2,000 trucks parked curbside, and then the more than 90 trucks were double parked when NJTPA conducted truck parking related research back in 2015. And then I-287 in Mahwah has some sort of the trucks frequently parked illegally on the shoulder area with the kind of roadway with the very steep inclines and then lane drop, which reduced from the 3 lane to 2 lane, which made some sort of spill back to the main line of this turnpike area there. So with that, the overall status of truck parking in New Jersey, it has some sort of significant shortage of parking space across the state. So again, the NJTPA identified the following 4 areas in New Jersey that have the biggest need for the additional truck parking space, such as interchange area of I-78 with the turnpike, and then I-287 corridor, which has only one or two available rest area there, and the city of Newark, and there are the area surrounding the Vince Lombardi, the rest area on the turnpike. So one way to deal with this kind of issue properly is to use a truck parking information system. But the New Jersey truck parking information systems would look actually challenging, because first of all, there's no, as far as I know, no official truck parking information system that can provide real-time parking information. But there are several websites or the mobile applications like a Trucker Pass, as shown on this the illustration here. But these applications or website has some limited, and then the information is not always up to date, because many of these applications are heavily relying on truck drivers' kind of input with respect to the availability of truck parking spaces, just like wage, which is provided by the driver's input for the accident, incident, or the other congestion. So to handle that the truck parking space issue, the NJDOT initiated a TPIS pilot study. That proposed TPIS pilot study is envisioned to be a tool for truck drivers and operators that can help them obtain a reliable information on the location and the availability of safe, convenient, and truck parking facility along their travel route. It is also designed to have ability to collect instantaneous data about parking spaces for truck, and then a way to disseminate the information in real time or pseudo real time to the trucking the community, especially the truck drivers, through a variety of different the dissemination methods like dynamic message signs, smartphone application, and traveler information websites like 511. So it is also designed to assist truck drivers proactively plan their route and then decision on parking to make it a little bit more safer and smarter. So we also hope to have the TMC operator having more instantaneous or accurate information about the truck parking availability, so that they can make some sort of the action or decision to mitigate any potential congestion caused by truck parking. So, this is the high-level system architecture of the proposed the TPIS, the pilot study. The system we proposed consists of three major subsystems. First, the data collection subsystem is responsible to collect definitely data and then monitor the current parking spaces availability, and then analyze the data to come up with what is the current available parking spaces to check the occupancies of spaces with trucks. And then data management subsystems basically archive the collected and analyzed data to a well-organized database, and then used to query the data for the users outside of the system. And data broker subsystem is going to be used to convert this collected data to be used for the user who wanted to utilize this information for the provision of the parking availability to the truck users, truck drivers, and operators as well. Well, here I have to mention for this presentation today, I mainly focus on parking detection technology with the highest focus on this, the vision-based one. So we try to, as part of this the pilot project, try to improve the performance of vision-based parking detection method. So the rest of the presentation will be mostly talking about that part. But we considered the sensor-based the detection technology. The one we are planning to use is sensor. The sensor can be either intrusive or non-intrusive, depending on how it actually works. For example, like a loop detector or range motion sensor, intrusive sensor can be used, but it requires some sort of road work because they need to be buried on the pavement, surface of pavement. So we are considering some sort of the latest of the magnetic field sensor unit, like the Sensis POC, that to be placed on each the parking space for this the pilot project. And then non-intrusive sensors also can be considered, like the radar sensor, microwave sensor, ultrasonic sensor, something like that. Well, both intrusive and non-intrusive sensors is known as to be less sensitive to some external factors like weather, illumination, or occlusions, the effect compared to vision-based detection. But it is also known that it is a little bit expensive than the vision-based detection because it requires some sort of the installation cost and the maintenance cost as well. Well, the vision-based detection is also considered as well, which the vision-based detection utilizes obviously the camera, but the one single camera can monitor the wider area, covering multiple parking spaces together, unlike the sensor-based detection. Well, but the vision-based detection can be more susceptible to weather conditions, and then its accuracy can be affected by various effects in the environment, like shadow, occlusions, and then pixelations of lighting, and even the perspective, the distortion of the video images as well. But this one is a non-intrusive, so obviously it's a little bit easier to install and then maintain, and then less the cost effective. Recently, the vision-based detection regained a great attention with the recent drastic advancement of the object detection techniques coupled with the deep learning technologies. So we then take this way, coupling the deep learning technology for vision-based detection with object detection techniques. So let me briefly talk about the meaning of object detection here. Object detection is a computer vision-based techniques for locating instances of object in either images or the videos. Like a human who are able to quickly recognize and locate object within of a certain interest within a very short time interval. The goal of this object detection is to replicate what the human intelligence doing by using a computer with some machine learning or deep learning techniques. So you can see, as you can see here on the illustration on the right side of the slide, this is one example of object detections, which shows 3 different components: trucks, bicycle, dog, detected by the computer who has been trained to detect this kind of object there. So object detection is now a key technology behind artificial intelligence applications like self-driving cars, drone, and robots. And then more recently, object detection is also very useful in applications such as traffic or video surveillance or image retrieval systems as well. There are several different models to deal with these object detections, and then for this project, we adopted the YOLO model, which stands for you only look once. Well, YOLO is a deep neural network for unified and real-time object detection. So I said here neural network, which is the same as a certain kind of the brain. So the model who developed people who developed this model made some sort of trained the neural network to be used for the major framework to conduct object detection. So YOLO is designed to detect multiple classes of objects all at once at the astounding processing speed, like a minimum 45 frame per second and up to 15 or 155 feet per second, really fast. And then now it is applied to a variety of applications, including autonomous vehicles control, and then automated security monitoring and traffic surveillance as well. So here is the one examples of YOLO-based traffic surveillance developed by NJDOT a couple of years ago. It shows that the video is keep kind of the moving because it was recorded by a person with their hand, his hand. So the video itself is not that very stable, but still the detection of vehicles are quite well. So that actually makes some difference compared to conventional video analytics with respect to traffic surveillance. So with YOLO-based truck detections, we conducted a proof of concept test to check the performance of the truck detection method within the truck parking information system pilot study. The pilot study location is Harding truck rest area on I-287 northbound corridor in Morristown. That truck rest area has 22 designated parking space. It is actually used by not just only trucks, but also non-truck vehicles like the van, the passenger cars as well. And then one of the most critical problem and issues of this parking space is that it is all the time filled in the evening hours and during the nighttime on a daily basis, and it has a frequent occurrence of illegal parking along each internal and external pathway. So it often makes some sort of spillback from the parking rest area to the main line 287, causing some sort of the congestions on the main line as well. So with that, for the proof of concept test, we developed the data flow as shown on this slide. Using IP cameras, they get the images for each the interest area, and then get all the images together, and then send them to the NJIT TPIS server to conduct object detections through through a 4G LTE modem. I mean the 4G mode, the communications. So with this data flow, we required the equipment to the pilot project site with the great support from NJDOT. So we then placed 7 IP cameras on the site here. As you can see, the small numbered orange, the circles indicate the location of each camera there, and then the box with the capital C indicate the cabinet which hold the power supply and 4G LTE modem, and then the PoE switch to provide the power to each the camera there. And with that, then this is an actual deployment of equipment on that the test site. Well, for the camera 1 through 3, we had to use a mobile trailer with a solar panel because that area has no available power for us to use. So the camera there, is now is powered from the solar battery equipped on this trailer. But the rest of the camera located on the rooftop of this the SSB team of this the rest area. Fortunately, we were able to get a power source on the rooftop, so we placed this kind of the cabinet there, and then with this modem and then the PoE switches, and then we were able to get the video images reliably, and then we can save, transmit each image to the NJDOT server. So with that, we conducted preliminary evaluations to get the YOLO-based truck detection. So here's, I showed you guys the most desirable performance of this, the method here, which was captured during the daytime. So each camera actually successfully detected all the trucks captured in the camera angle, which is good. So with the day is all the time the beautiful like this, then probably our detection system will be perfect. But well, another case still, I believe, I hope, acceptable with respect to its accuracy. But this result shows. This slide shows the result of the truck detection captured day, but with rainy conditions. So you are able to see some water droplet on the faces of the lens of some the cameras there. So some cameras with some the water drips have some missing the trucks detected here, but still it is able to maintain about the 80 to the 90% of the detection accuracy as well. But the worst condition happened during the nighttime with rain, just like yesterday night. So well, there are a lot of some sort of kind of the blocks making the cameras properly capture the scenes because of just the simple the water droplets on the faces of lenses. So that made the system lose some trucks detected, as you can see here on, for example, camera 7. The trucks on the middle of the angles are completely undetected, and then camera 4, the trucks in the middle as well was not able to be detected as well, just because of the water on that the lens. So, well, with that, I would like to summarize what we have done. As I said, what I showed you today is the part of one of our ongoing project. So maybe we will have more chance to do more to get better result. But well, as a conclusion, I would say we developed a vision-based truck detection method using one of the cutting-edge object detection neural network model, and then applied it to the proof of concept test for the New Jersey truck parking information pilot projects as well. And then they evaluated the performance with several different conditions, and then the overall the detection accuracies ranges from 65% to the other 97%, depending on the conditions like weather, visibility, and others. And the worst performance that were observed during the nighttime with bad weather conditions, as I show you. But compared to conventional video analytics, which was very sensitive to various external factors like image occlusions, vacillations, and shadow effect, and others, well, this object detection method are less sensitive to those side effects. So I think I met the presentation time given to me. So I think this is pretty much of what I prepared for the presentation today. So if you have any questions, please feel free to let me know.
We do have time for one quick question, and it was, what was the tracking method implemented with a YOLO detection?
For this, the truck detections, if the question is about these truck detections, we did not apply the tracking method. We just detect and then check the changes of bounding box center point. That's it. But as I shown you here in this traffic data surveillance, this one we used the tracking method, but I forgot the name of that tracking method.
Okay, we have now arrived at the final technical presentation titled Automated Analysis of Surrogate Safety Measures and Non-Compliance Behavior of All Road Users at Intersections, presented by Dr. Deep Patel of Rowan University.
Hello everyone, good morning. Today I'll try to talk about one of my research topic, automated analysis of surrogate safety measures and non-compliance behavior of road users at intersection. Myself, Deep Patel. I am a graduate research fellow and a PhD student at Civil and Environmental Engineering Department, Rowan University. And my advisor is Dr. Muhammad Jalayar. He's an assistant professor at Civil and Environmental Engineering Department, Rowan University. So today, I will go over to the following parts of my research. I'll go over to the introduction of my research, literature review, research objective. Would highlight some of our data collection method that we did and what kind of data we collected. Draw some highlights of video analytics AI framework that we developed at Rowan, basically. Then would try to discuss about some of the safety analysis parameters that we are evaluating using this tool, and then provide you with tool output, demonstrate a little bit of tool output, and show you some results, like test results that we performed on a sample video that we collected from the nearby intersections of the Rowan University, and would like to draw some conclusions based off it, and then try to discuss about the questionnaires if any participants have. So thank you so much for coming today, first of all, and then let's get going. So introduction. So according to the National Highway Traffic Safety Administration, in 2018, there were 14,711 fatal crashes that occurred at or near to the intersection, which has an involvement of vehicles in it. And everyone knows this thing. So every year, over 2.5 million intersection-related crashes are reported. But however, there are numerous crashes at the intersection that did not result into the major injury or damages, are sometimes not recorded or sometimes not reported because of various reasons, weather or some kind of lifetime conditioning, and all of those issues are, and those crashes are not recorded, right? Towards which, as a part of our research, we did some literature review, wherein we had a very comprehensive literature review of nearly 35 to 40 papers in it. And this is just the highlights of few of the papers that do as a video analysis part, does the surrogate safety measures analysis using a video at an intersection, basically most of the time. And those are the parameters that are been evaluated through those literature, those studies, basically. Yeah. So moving forward to our research objective. So with an aim to evaluate the traffic operations and safety of the transportation network, we developed a machine learning algorithm to analyze video data that captures the traffic volume and traffic conflicts, wherein an AI framework that works for different road users and calculate safety measures were also integrated in it. To which we had some potential data collection that we were required for the safety analysis. So wherein we used a CountCam 2 traffic recorder cameras, which we mounted it onto the nearby poles of the intersection. and then we try to record some video from which has a top angle view, and then we collected some crash we collected some of the data such as conflict point, speed of the vehicle, traffic volume, road users, and then the signal indicators based on the video part. And then we also looked over to the crash data to see that okay, what are the potential crashes at that location are. So that would be one of the parameters that can help us to select the intersections which require more focus on, basically. So moving forward to our video analytics AI framework, I would like to just draw your attention on to how our process works and how the analysis goes on. So we just input a feed of a video. It can be an extension to .mp4, .avi, or any kind of extension, any extensions are acceptable on this one, wherein we import a pre-trained models and weights that were being developed during the analysis part of development of one of the very nice detection algorithm, that is you only look once, that is YOLO. YOLO is a framework, is a process that does a very simple regression, is a kind of very simple regression problem and does not require any kind of complex processing structure in it. In addition to that one, the advantages are YOLO is very fast, it quickly identifies the objects in the frame. It can process recorded video and can also be used for real-time detection analysis, as it has a really good detection speed, basically. Wherein further, after importing the pre-trained models and the weights, we read the video frame by frame, and using the detection algorithm, it does the detection of the all road users with their classification that this is a person, this is a truck, this is a car, whichever the road user we see over there, right? So majorly is categorized into these three aspects. Out of that, we extract out the volume and the speed of the traffic flow. So that's volume would be the count of that each vehicles that we see entering the intersection. And then we also extracted out the trajectorial data. That's the X and Y positions of each and every detected object in respect to the time, basically. And then further, we manually validated the outputs, saying that are those outputs correct or not? Are they having some errors, or are we getting some wrong values or something like that? And then we try to evaluate the surrogate safety measures based on the guidelines that we have from the FSW. So as a part of our safety analysis, we collected traffic counts, wherein it consists of the classification of road users, total number of vehicle entering the intersection, total number of pedestrian crossing at or near the intersection, and then and we had a count base also on the directional of the traffic flow. So it's north to south, or south east to west, west to east, whichever direction it was going, or it was from north to east if it was a turning movement. Then so you can see a demonstration of that over here. So if you see that 3 cars went, so we have counted the total cars over here, total object counted, and then in that each frame how much cars were present in that thing for our back-end purpose analysis. So we are counting that also. So further, we also evaluated the violation and non-compliance events. So if there is a violating vehicle or something like that, so the count of vehicles violating the running red light signals, then count of pedestrians who are doing jaywalking or something like that. So if you look over onto the right hand side picture, now you see this blue car coming and then it turns red. When it turned red and that passes to that green line, it was considered as a violation because it passed that line when the signal turned red. So it does the evaluation of both the aspects and try to provide us saying that, okay, this was a violation. So this was just a sample to show about one of the prospecting, but we are evaluating for all the 4 aspects based on the signal values that we have. Further moving forward to the main objective of the safety analysis are the surrogate safety measures, basically. So we calculated time to collision and post-encroachment time. And we also evaluated travel path of all the road users to evaluate and see I like to examine the conflict points and to calculate those, okay, what are the potential conflict points at that intersection. So further moving on to that side, so towards looking over to the definitions of TTC. So TTC is defined as a time that remains before 2 road users collide unless one of them takes or avoids the manipulation such as by manipulation such as braking or reducing the speed or by changing lane. So wherein I'll try to show you some graph thing like in respect to space and time. When we have a very strict defined conflict point, as I mentioned previously, like when you see that there are like multiple areas where you see this is the conflict point, this is the conflict point, this is the conflict point, and this is a predefined area basically over here. And then in respect to time, we see that time frame from T1 to T5. And if we consider T1 to be the encroachment beginning time for the vehicles, so if we suppose there were two vehicles that entered the intersection, so one was the through vehicle and the other one was the intersecting vehicle that were entering that part. So what happens is that before reaching that conflict point, what it supposes, this is the thing, that if it reaches that conflict point, one of the vehicles is definitely going to reduce the speed so they do not crash or collide with each other into as a safe maneuvering. So what happens is this thing. How about if we suppose that one of them was distracted, one of them had some issues with the braking or did not consider or had a misunderstanding with the other vehicle that was on the other side and didn't understood his signal. So what might happen if it did not reduce the speed? So if we look over to that part, we try to project project the arrival time of that conflict in, like, if that speed was not changed compared to the previous one. So what might happen is that it might crash or it might reach to the point where it was a nearly miss crash. So like there was nothing happened, but it was very near close interaction between those two vehicles and then they passed safely. But those all kind of parameters, when the threshold value is less than 1.5 seconds, so what we say is this thing, like if the difference between those two timing periods is less than 1.5 seconds, it is a risky behavior that is being seen at an intersection. And when like the crashes that occurs most of the intersections, they have a higher risky behavior part where some of them leads to the crash and some of them are safe. But sometimes those parameters have been ignored over there. Looking further, I just want to demonstrate it, right? Like if you see this video would give you a visual interpretation of what I was trying to describe. So if you look over to this video, so if you see into this one, there is a pedestrian who is trying to cross the area, and then there is a blue car that came from here. And if you see this part, that what if that blue car did not put his brakes, did not apply some brakes on it, right? So what might have happened? So if that was if he did not apply the brake, then it was a nearly missed thing. So the difference between the crossing that same point, the conflict point from here, this guy passing from here to here, and then the car reaching at the same, if the speed was not like if he did not apply the brakes, then what might have happened? So this is something like it is a nearly miss event, so that would be like 1 second of difference among them. And then further moving, we also evaluated the post-encroachment time. Post-encroachment is a time between the leaving of the encroaching vehicle from the conflict point and the entering of the other vehicle, or a pedestrian, or pedestrian leaving and a vehicle entering. It can be vice versa, with an appropriate way at a conflict point. So like just going back to our again to this example of time and space in the graph thing, we have a fixed defined conflict point, and then we have in respect to the time T1, T2, T3, T4, and T5, and then we look over to the encroachment beginning time. So over here we are not predicting anything, and we are just seeing the time difference of two vehicles entering and exiting that same point. And what we see is this thing, vehicle or pedestrian, both, like basically. So what we see is this thing, that the time difference between them, like if we reduce the time from T5, like T5 minus T3, if the values are less than 5, it is considered as a risky behavior. And if those values are even less than 1.5, it's a really high risky behavior, and that might someday cause this kind of behavior. Such behaviors might cause a crash at that location basically, and would be a potentially high crash location. So now I would like to demonstrate you with our tool outputs, how does that work and how it is like functioning basically. So if you look over to this video over here, you would be able to see this video, right? So if you look over to this video, see this. This is a safety analysis tool that has various parameters saying that you can analyze the pedestrian volume, vehicle volume, directional base volume, pedestrian violation, vehicle violation, time to collision, post and collision time. So in this one, you just need to upload a video with whichever extension you want. And this location is just the name of the file that you want to define after, like when it creates out the report, what should be the file name coming out. And at simultaneously with the analysis part, you would be able to see such kind of graphs being extracted out. So in respect to the time, this is just a sample graph that I have created from like a large video to the shorter one, basically. So to see this thing, you would be able to see that thing, that the vehicle red light violation just went on going. And then what happens is this thing that when you just try to move further, like every time the vehicle volume started increasing as the vehicle started entering the intersection at a time difference of 5. And then if there is a violating vehicle coming up in that area, you will be able to see that, okay, this is violation now. So violation stepped into this one, and then you move further. So this is the way that we do this part, and then it's a good demonstration of both the things, and simultaneously you can even see how the analysis is working. Towards which we had a test. We created a sample test. We captured a video at the Carpenter Street and the Hudson Road in Glassboro. So it is an intersection. It is a signalized intersection near our university. So where we mounted up the camera on one of these poles over here on the side, and then we tried to capture the whole thing that you were seeing as the analysis part. And the results were like, okay, we had a video length of 30 minutes, video resolution of 640 x 480, and frame rates were 10 frames per second basically. And the results were output were like, there were like total vehicles were like recorded to be 362, wherein left turning vehicles were 57, right turning vehicles were 87, through vehicles were like straight vehicles were 216. And then red light running vehicles, like, so this is the violating part basically. What was the violation scene? So there were like 7 vehicles who crossed the intersection or entered who entered the intersection basically, because as to our algorithm is like, when you enter the intersection, it will, and if it was red, it will consider that it is like you did a violation. And then further we counted the traffic volume. Due to certain reasons it was low of pedestrian, but usually it is high, but might be due to the reason it was evening, and as right now the universities are not like, it's working online, so might be the reason, major thing. And so if you look over to the jaywalking events, out of 6, 4 were jaywalking events. So that's a major thing that we can evaluate, saying that, okay, the behaviors of pedestrians, they do not use crosswalk or something like that over here. So in terms of the risky behavior part, based on the TTC, based on the TTC, like, which has a threshold value which is less than 1.5 seconds, there were 12 events that were recorded that way in a 30 minutes of video. And high risk behavior, like high risky behavior, as per to the PET part, where it is less than 1.5 seconds, there were 16. And nominal risky behaviors, but this is called a risky behavior, as per PET, which was less than 5 seconds of threshold value, were 59 events that were recorded for the part. Moving further, we concluded some of this thing. I think that the algorithm demonstrated, like for us in this video, that the algorithm demonstrated more than 98% of detection accuracy for the tested video. And safety analysis parameters can help in investigating the relationship between the human driver behavior and the collision risk at an intersection. So overall, the developed tool would help the State Department and the State Department of Transportation and the local agencies evaluate the intersection safety with less effort, and like would be not that complex thing that, okay, you need to do a lot of calculations at the end. No, it would really help us out to do a quick calculation and try to evaluate, saying that, okay, what it is. And in addition to that, we can also do the real time, seeing that, okay, what's happening right now. And towards which I would like to acknowledge our sponsor and thank them for funding us with this project, Region 2 UTC Center Rutgers, and our research team, Dr. Nidal and Dr. Rasul Ghulam from our EC department at Rowan University, and one of the research fellows of ECE, Abdul Qadir, and Nima from Nima, one of our computer science students. So thank you, everyone. So let's open up the question session. So does anybody has any questions or anything like that?
So thank you very much for answering all these questions as we've been going through. One of them was, what do you consider jaywalking this close to the intersection?
Yes. So thank you everyone, first of all, for listening to my video session. So onto that question. So for us, when we were considering the jaywalking for the pedestrian part, we tried to look over to the pedestrian who, how many pedestrians use the crosswalk or they walk outside the crosswalk, and in respect to the traffic signal also. But we did not consider about the countdown clock parameter that says when you start when the countdown clock comes onto the pedestrian side, you should not start walking. So we did not consider only that parameter, but the signal was signal condition was being considered, and if the pedestrian is using the crosswalk or not. That these were the two major conditions that we had used for defining that it was a jaywalking or not.
Were you able to run this with any video, or do you have to use special equipment?
So in terms of the extension file, we can use any extension of the part. The main purpose, the main major requirement is we should be able to even see the traffic light. That's the major thing, because when you try to evaluate the other perspectives, it's possible to do it with any kind of videos. But for the violation part and evaluating the violator, we at least should have a visual of one of, out of 4, one of the traffic signals should be seen in that whole camera vision. So we can try to provide conditions based on that thing to evaluate the all 4 approaches. And in terms of resolution, the lowest I think is 320 cross which was acceptable condition for the detection. So the lower the resolution, the lower the accuracy, higher the resolution, the higher the accuracy. That will start working, but the accuracy level would drop if the resolution is not good.
Okay, thank you, Dr. Patel and Dr. Lee from the previous presentation. We will now move on into the third part of our virtual poster session. The poster presenters will have an opportunity to respond at the conclusion of the 3 presentations. Our first poster presentation is titled Thermally and Mechanically Balanced Structure Design of Insulated Pavements for Cold Region Applications, and is being presented by Rowan University's Zhang Zhou.
Hello everyone, welcome to my section. My name is Zhuang Zhuo, and I'm a PhD candidate of Rowan University. The title of my study is Thermally and Mechanically Balanced Structure Design of Insulated Pavement for Cold Region Applications. The insulated pavement is a special pavement structure that adding a thermal insulation layer above the frost susceptible layer. This method has been proved to be an efficient strategy to mitigate the frost effect on pavement in cold regions. However, no much effort has been conducted on the design of this insulated pavement. For this reason, the objective of this study is to propose a thermal and mechanical design approach based on the novel finite element model. The flowchart of this study is presented in the left corner of this poster. Firstly, choose the design criteria and reliability level based on a specific project. Then select a trial design structure using a proposed finite element model to predict the thermal and mechanical responses, and then predict the performance based on the responses. The numerical model and the loading area are listed right next to the flowchart. To validate the accuracy of the proposed numerical model, 2 large-scale pavement boxes were built as shown in the middle part of this poster. One as a control sample without any insulation layer, and the other is an insulated pavement box. For each box, the side and bottom were thermally insulated to make sure that the heat transfer process only happens on the top surface. Several thermocouples were placed inside the boxes to monitor the temperature changes with time. After finishing the boxes, a cooling system was placed on the top of each boxes to freeze the whole structure. Then the test results were compared with the predicted values given by the proposed numerical model. The comparison was presented at the bottom of the middle part of the poster. It can be seen that the finite element model can give a very accurate temperature prediction. The R-squares of the predicted value and the actual value are all bigger than 95%. Besides, the predicted stress and strain were compared with the KMP. The comparison is also listed on the bottom of the middle part. With the validated finite element model, the thermal and mechanical responses.
Our second poster presentation is Climate Change Impact on Pavement Overlay Performance with Adaptation Strategies. The project is being presented by Xiaodan Chen of Rutgers University.
The effect of warming temperatures due to climate change will increase the risk and the vulnerability of road pavement. So there is a need to proactively address the risk during pavement design process and to enhance the resiliency of roadway pavement in New Jersey. This study aims to quantify the impact of warming temperatures on flexible pavement overlay performance and to evaluate the feasible adaptation strategies in response to climate change. The methodology mainly includes 3 steps. The first step is to perform local calibration of pavement ME design software. The calibration models include asphalt layer rutting, fatigue cracking, and transverse cracking. The second step is to prepare historic and projected temperature data for simulation inputs. The projection of future warming temperatures in this study was sourced from 32 global climate models under the representative concentration pathway 8.5. And the final step is to compare the pavement performance using historic and future temperatures input and to propose potential adaptation approaches. The result shows that warming temperature contribute to the faster pavement deterioration, especially for fatigue cracking. The predicted pavement overlay life decreased by 2 to 3 years due to climate change. So we proposed 2 adaptation strategies. The first one is to increase overlay thickness. We found that with an increase of overlay from 6 to 7 inches will extend pavement lives by 3 to 4 years, and at the same time would reduce the annualized agency cost up to 9%. The other effective adaptation strategy is to reduce in-place air void from the aspect of construction quality control. The results indicate that 1% reduction in air void will be sufficient to mitigate the negative effect of warming temperatures and even slightly increase the pavement overlay life. The major conclusion of this study is that if pavement engineers still use historic climate input in future pavement design, it will be very likely to overestimate the pavement surface life. And the proposed adaptation strategy provides practical solutions to preserve long-term pavement performance under warming temperatures due to climate change. Thank you for listening.
Okay, our third and final poster presentation for today is entitled Implementation of Porous Concrete in Sidewalks in New Jersey, presented by Kathleen Stavoli, Jack Cannon, and Luke Dragon of Rutgers University.
We are the Implementation of Porous Concrete in Sidewalks in New Jersey. I'm Luke Dragon.
I'm Kathleen Stavoli.
And I'm Jack Cannon.
And we're working with a graduate student, Hardik Yagnik, and Dr. Hussam Najim as part of the Civil and Environmental Engineering Department at Rutgers University. So pervious concrete has been gaining popularity as a potential solution to reduce puddling, lower the amount of impermeable surface area associated with sidewalks, recharge groundwater with efficiency, and slow stormwater surface flow rates. As important as these benefits are to surface runoff mitigation, there are concerns as to the ability of pervious concrete mixes to provide sufficient structural support and longevity for the expected service lives of the sidewalks. In this project, porous concrete will be implemented in sidewalks in the Skillman Pathway project in Montgomery Township. The purpose of the implementation is to evaluate construction practices of porous concrete, study maintenance methods to avoid clogging from debris sediments, and study resistance of porous concrete in sidewalk to potential raveling, as well as the effects of freeze and thaw conditions on de-icing salts. Periodic field infiltration tests will be evaluated to changes in void ratios. The Rutgers research team is also evaluating several porous concrete mixes that are designed to improve strength. In particular, the research team is evaluating the effects of adding specified percentage of sand to the mix and the effect of compaction methods on strength and void ratio. Skillman Road and Pathway is a Rutgers implementation of 4 of our different mixes to be used for sidewalk reconstruction. It follows the NJDEP drainage and NJDOT strength guidelines for a 10-year storm event. The path is 400 feet long and 6 feet wide and runs alongside a large green area. This will be the first long-term implementation of our mixes and will illuminate our highest performance mix for the future full construction.
To determine which porous mixture would be the best, we tested a variety of different mixes that were prepared in 4-inch by 8-inch cylinders and set to cure in a controlled laboratory for 14 days. Each pervious concrete mix was composed of cement, water, and 3/8-inch aggregates. To further our research, we incorporated tests with sand. From these tests, we wanted to see how the sand would affect void percentage and alter the performance of the porous concrete samples. Since porous concrete is composed of larger aggregates for each separate mix, our biggest obstacle is how we plan to vibrate the samples. Vibrating the samples like normal industry practice would cause the components to separate. So we use different rods and compactors, as seen in Figure 6, to determine the best way to vibrate the porous samples. The figures display show how samples were prepared and tested in the laboratory. After testing the various porous samples, we gathered consistent results. As we increased the sand percentage, which is traveling down the columns of the charts, we discovered an increase for the compressive strength and a decrease in the void percentage. On the contrary, as we increased the diameter of the vibration rods and compactors, which is traveling right on the rows in the charts, we saw a decrease in compressive strength and increase in void percentage. For the cells that are left blank in our charts, we are still pending test results as the porous concrete samples are still curing in our laboratory.
Now, if you focus your attention to the hydrological design section, we could see the different hydrological designs that were performed to study the variation of the reservoir layer thickness, denoted by the letter T, with different factors such as storm return period and porous retention area, which is denoted as PRA. From the top left picture, you can see the typical cross-section of what a porous concrete sidewalk would look like, with the porous concrete on top, the storage layer below, and the soil as the bottommost part. The soil type is very important for the success of the drainage. The soil has to endure a 72-hour drainage test to see if it can absorb a specified amount of water in the given time. Luckily, as Melik Tully has found through their soil logs, the soil we are dealing with is a soil group B, silty loam, which is decent at draining, unlike clay. Then, if we glance at the graph below, we can observe the relationship between the thickness of the storage layer and the return period. The greater the return period, the greater the required thickness of the storage layer. As Luke had mentioned, we are considering the 10-year storm event. Similarly, if we look at the top right image, we can see the greater the porous retention area, the required thickness decreases. The bottom chart then summarizes our different variations of thickness, porous retention area, and return period. To summarize, although our research is not finished, we have made significant findings. For instance, we found that the best vibration compactor would be the 2-inch compactor, and we are very hopeful to see those finished results and see if they meet the final result parameters. We will be continuing with this research next spring and testing different variations of our findings. Thank you.
We actually do have a question in relation to this last one, so I'll read it, and if one of the 3 participants can read it, I actually got a few for coming up. The first question is, does any porous concrete or asphalt need to be cleaned regularly to make sure that the pore spaces allow the water infiltration?
Yes, Dr. Najim has stated in the chat, it does need to be regularly cleaned as that drainage rate, right, as he says, the pressure cleaning. We use like a water jet to shoot out and clean the pores, as well as it needs to be maintained to ensure that drainage rate is high to ensure the 72-hour limit as per NJDEP.
Another question, person's wondering how porous will a typical sidewalk, how are they, and how much better would drainage be with a porous sidewalk?
Well, typical concrete doesn't really allow for any drainage, so this concrete would be it's essentially a cheaper drainage solution than conventional piping, and it prevents ponding. So it'll allow for that kind of alternate material solution for construction.
Yeah, to add to that, Luke, also the concrete itself has more basically holes and air, gaps and spaces for water and different materials to flow through. So essentially, it just acts as a natural filtration system as opposed to having to install like a really expensive system underneath the concrete itself.
Okay, this concludes our event. On behalf of the New Jersey Department of Transportation, we'd once again like to congratulate all the award winners and thank all the presenters for making this year's research showcase a success, especially under these challenging times. We hope you enjoyed the event. We will be posting presentations and responses on the NJDOT Technology Transfer website. A link will be emailed to all attendees along with your certificates of attendance. Thank you and have a nice weekend, everybody.